Let me first say a couple of words, Bruce. Welcome, everyone. This is April edition of the mini-school that will be given by Professor Bruce Watson on vector lattices with a view to applications into stochastics. We look forward, Bruce, for your mini-school.
Thank you very much. And it's good to be presenting at NITheCS, the NITheCS mini course or mini school. And this is the first of a series of lectures. And in this lecture, we will be looking at the basics of what is a partially ordered space, what is a lattice, what is a vector lattice, and some of the basic definitions of things like suprema, infima, maxima, minima in this partially ordered setting. So we are not presuming specialization in any particular area of mathematics for this talk. So I will take things carefully. A partially ordered set. So we obviously want the set to be non-empty, otherwise it's going to be rather trivial and pointless. And we put a relation on there, which we can call predecessor or below. And that's indicated by this squiggly less than sign. And a relation is a subset of the Cartesian product. A relation on A is a subset of the Cartesian product of A with itself. And we say that X is related to Y if the ordered pair XY is in the relation set. Okay. And that is our third bullet point here. And what we're interested in for this talk are relations which are called partial orderings on the set. And these have three properties. You require that each element of A has to be related to itself. So each element X in A is a predecessor of itself, X. Secondly, we require transitivity. That means that if we have three elements from A, and if X is below Y or a predecessor of Y, and Y is a predecessor of Z, then we can jump over Y to get that X is a predecessor of Z. And the last property we require is that of antisymmetry. So if we have X and Y in A, with X being a predecessor of Y, and Y being a predecessor of X, so if X is both a predecessor of Y and Y is both a predecessor of X, then X and Y have to be the same. They have to be equal. Partially orderings, those people who know what an equivalence relation is will know that this is very similar to an equivalence relation. The first two properties are the same, and we don't have the antisymmetric relation. Instead, we have a symmetry type relation or equivalence. But we're interested in partial orderings here. And let's look at a stock of examples of these. The most well-known and easiest is the real number system with the relation of less than or equal to. So if you have two real numbers and one is less than, or if one of your real numbers is less than or equal to the other, well, let's have a look here. Each real number is less than or equal to itself. If you have three real numbers where one real number is less than or equal to your second real number and your second real number is less than or equal to your third one, then the first one is less than or equal to the third one. That's your transitivity. And thirdly, if you have two real numbers, X and Y, and X is less than or equal to Y, and Y is less than or equal to X, then X equals Y. So there's your probably best known example. and one of the core examples. Now, what about sets? If we have a set and we take the power set of X, that's the set of all subsets of X, and then we can partially order the power set of X by set containment. So if we have two subsets of X, we say that A is below B if A is a subset of B, where A and B are subsets of X. That induces a partial ordering on the power set of X. Another useful example of a partial ordering is Rn with component-wise ordering. So we say that the vector X is below the vector Y if each coordinate xi of X is less than or equal to each coordinate yi of Y. So xi is less than or equal to yi for each I, going from 1 to n. And that gives us a partial ordering on Rn. But that's not by far from the only way you can partial order Rn. There's another useful one, and this is the type of ordering you use when you organize books alphabetically, or any object alphabetically. You start out by comparing the first letters of the word. So you think of x1 through to xn as a word, and y1 through to yn as another word. And we say that the word X is a predecessor of the word Y if, and let's go along, we go along and we check the letters. The first letter, is the first letter the same as the second letter? If so, we progress to the next letter. If the first letter is a predecessor of the second letter, in other words, because we're working on Rn here, if X is less than or equal to Y, less than Y, if x1 is less than y1, then X is a predecessor of Y. If X equals Y, we step on and consider x2 and y2. If x2 is less than y2, then we say that the word X is a predecessor of the word Y. And we continue all the way along, and if we get them all the same, then they are equal, and so X is still less than or equal to Y, or predecessor of Y. Otherwise, at some point, we have a strict inequality for some j, where xj is below yj. So that is, if you like, alphabetical type ordering, or lexicographic ordering. And that gives you a different partial ordering on the reals. Well, one of the first things one notes when looking at partial orderings, there's a reason why they're called partial orderings, and that is not every element has to be comparable with every other element. And we say that two elements, let's say X and Y from A, are comparable if either X is a predecessor of Y or Y is a predecessor of X. If all the elements of A are comparable with each other, so for any X and Y in A, we have that X is either less than or is a predecessor of Y, or Y is a predecessor of X, then we say that A is linearly ordered. One example of this is the real number system. The real numbers are linearly ordered. If I give you any two real numbers, X and Y, you either have that X is less than or equal to Y, or Y is less than or equal to X. If we have, let's progress now to Rn with component-wise ordering. This is not linearly ordered. Take, for example, the two vectors in R2, the vector 0, 1 and the vector 1, 0. Well, are they comparable? 0 is less than or equal to 1 when we compare the first terms, but 1 is not less than or equal to 0 when we compare the second terms. So let's try them the other way around. Is 1, 0 a predecessor of 0, 1? It's not, because 1 is not less than or equal to 0. So the vectors 0, 1 and 1, 0 are not comparable in R2 with component-wise ordering. Now, if we consider Rn with lexicographic ordering, we see that indeed Rn is now linearly ordered, because any two words or vectors in Rn are comparable with each other. We'd look at it for the case of R2. So what do? We go along and we check whether x1 is less than or equal to y1. If x1 is less than or equal to y, or if x1 is less than or equal to y1, if x1 is equal to y1, we progress and we look at y2. If x2 is less than y2, then the vector x is a predecessor of the vector y. If x2 is greater than or equal to y2, then y is a predecessor of x. So they are always comparable. Well, the next thing we need to look at are things like bounds, maxima, minima, and suprema, because we are hoping to get to the point where we can talk about lattices. So we start off with the set X. We have a partial ordering predecessor on it, and we take a non-empty subset of X. Okay, if there's some element lowercase x in X, so that every A from the set A is a predecessor of little x, then X is said to be an upper bound of A. And A is said to be bounded above. One of the things to note here is that for X to be an upper bound of the set A, we require that little x is comparable with every element of A. Okay, if X is an upper bound of A, and for each other upper bound Y of A, we have that X is a predecessor of Y, then X is said to be the least upper bound of A, or the supremum of A. And note the word the here, that implies uniqueness. This uniqueness comes from the asymmetry in our partial ordering, the asymmetry axiom of partial ordering. So note that for X to be the least upper bound of A, we require that X is comparable with every element of A, and X is comparable with every upper bound of A. So it's comparable with two different families of subsets of X. In other words, X is comparable, has every element of A as a predecessor of it, and every upper bound of A is a successor of X. But we cannot arbitrarily assume that suprema always exist, even if the set is bounded above. And we can define lower bounds and infima in a similar way by reversing the inequalities, the partial ordering. Okay, well, now let's progress to the term maximum and minimum. Now, again, we are still in the setting of a partially ordered set and a non-empty subset of X. Then we say that an element A, lowercase a, of the set A is a maximal element of A if for every element X in A, which is a successor of little a, we have that A is equal to X. So the only way we can be beyond the element A and still be in the set capital A is to be equal to little a. Okay. Well, if there exists A in A so that little a is comparable with every element X from A, then, and it is also that every element X of A is a predecessor of little a, then A is called the largest element of A. And again, there is uniqueness here. Again, and it comes from the asymmetry of your partial ordering. In this case, if the set A has a maximal element, has a largest element, little a, then A is also a maximal element of A, and it is the only maximal element of A. In other words, it's the maximal element of A in this particular case. And we can progress in a similar way to consider minimal elements and smallest elements. Now let's look at some examples. We're going to work with R2 with component-wise ordering because it's really nice and easy to work with. And we're going to take our set A to be the pair of vectors 1, 0, and 0, 1. Now, I claim that both of these elements, 1, 0, these vectors 1, 0, and 0, 1 are in fact maximal elements of A. Because, okay, we're going to show that one of them is, if I take the vector 1, 0 and require that 1, 0 is a successor of the vector x1, x2, where the vector x1, x2 comes from A, then we know that x1 has to be greater than or equal to 1, and x2 has to be greater than or equal to 0. But the only way I can get x1 to be greater than or equal to 1 for x1, x2 in A is by setting x1 equal to 1. But since x1, x2 is in A, that requires that x2 is 0. So indeed, 1, 0 is a maximal element of A. Because the only element of A that was a successor of 1, 0 was in fact 1, 0. And the same applies. You can do the same argument for 0, 1. So this shows, firstly, that A has two maximal elements, and that not all elements of the set A are comparable with the maximal elements. And neither of these maximal elements is an upper bound of A, because 1, 0 is not comparable with 0, 1. So you can't claim that either one is a maximal element of A. Now, when we're working with, let's return to this and look for the least upper bounds. So we want an upper bound for the set A from R2. So if the vector x1, x2 is an upper bound for A, then x1 has to be greater than or equal to 1 and greater than or equal to 0. And x2 has to be greater than or equal to 0 and greater than or equal to 1. So x1 and x2 are both greater than or equal to 1. So the smallest, the least we can take x1 to be is 1, and the least we can take x2 to be is 1. So let's check whether that is indeed an upper bound for A. We have that 1, 0 is less than or is below 1, 1, and 0, 1 is below 1, 1. So indeed, 1, 1 is an upper bound for A in component-wise ordering. Also, 1, 1 is not a maximal element of A because 1, 1 is not in A. Okay? And now, what happens if we take any other upper bound, x1, x2 of A? Then we require that 1, 0 is a predecessor of x1, x2, and 0, 1 is a predecessor of 1, 2, of x1, x2. This gives us that 1, 1 has to be a predecessor of x1, x2, giving that 1, 1 is the least upper bound. Because any other upper bound, our other upper bound, x1, x2, is comparable with 1, 1, and 1, 1 is a predecessor to it. So 1, 1 is the least upper bound or supremum of A. Now, our aim at the end of this mini course is to be in a position where we could start looking at stochastics via partial orderings and ordered vector spaces. So one of the things we need to do now is look at vector space structure along with partial ordering. So throughout this, whenever we talk about an ordered vector space or vector space, for the remainder of this, we're going to assume that we're dealing with a vector space over R, over the reals. That you don't have to do that, but certainly to get the wheels rolling, it's the best way to start. And we've assumed that the set E, this vector space E, is partially ordered by the relation predecessor, as given in bullet point 2. Okay, we say that E is an ordered vector space if we have the following compatibility conditions between the partial ordering and the algebraic structure of E. So it's not good enough just to have that the set E is a vector space and that it's partially ordered. There has to be a degree of compatibility between these two sets of processes, between your partial ordering and your algebraic processes. So what we require is that if we start off with X, a predecessor of Y, and we add any vector to both sides of that relation, add a vector Z, say, to both sides of that relation, we retain that relation. So in other words, we get X plus Z as a predecessor of Y plus Z. So this allows us to do what we are so used to doing in linear algebra, being able to add things to both sides of an equation or an inequality. The next one is that if we have two vectors, X and Y and E, and alpha a non-negative real number, and X a predecessor of Y, then multiplying X by alpha and Y by alpha retains that relation. So if alpha is greater than or equal to 0 and X is a predecessor of Y, then alpha X has to be a predecessor of alpha Y. This reminds us of elementary inequalities where you have that X is less than or equal to Y, and you need to be able to multiply both sides by non-negative real numbers and retain that inequality. We require that compatibility structure here. Okay, and since we've got partial ordering and we've got a 0 now because we're in a vector space, we can consider whether a vector X in E is positive or is above 0. So in other words, whether 0 is a predecessor of X. The set of positive elements will be denoted E plus, superscript plus. This has it's what is called a cone, but we will deal with that in the second lecture of this series next week. And so for the moment, we are just letting E plus denote the set of positive elements without talking about its structure any further. And one point of notation, we say that Y is a successor of X as being the same as X is a predecessor of Y, the last bullet point. Well, the stock of examples of partially ordered vector spaces is enormous. I'm just going to do a couple of well-known ones and useful and interesting ones for where we are going. One of the first examples, obviously, is the reals. The reals has everything we could want. It's actually linearly ordered. It's a vector space over itself. And the ordering, the partial ordering on the reals is compatible with the algebraic structure, making the reals into an ordered vector space. Rn with component-wise ordering is again an ordered vector space. It's just relatively easy to check. Rn with lexicographical ordering is a partially ordered vector space. That is not so easy to check. It takes a little bit more hard labor, and notation is a bit messier. And now the continuous functions, real-valued continuous functions over a topological space, omega, where we define the operations pointwise. So we mean that f is less than or equal to f is less than or equal to g. We take that to mean f of omega is less than or equal to g of omega for all omega in capital Omega. And we take that the algebraic operations to be defined pointwise. So f plus g acting on little omega is f of omega plus g of omega. And alpha f evaluated at omega is alpha times f evaluated at omega. And with these operations, C omega is an ordered vector space. Now, we can move up in level of abstraction now to the LP spaces over a measurable space. And now we are no longer working with actual functions, we are working with almost everywhere equivalence classes of mu measurable functions, where we've required that the pth power of the absolute value of the function be integrable. And all operations are defined almost everywhere pointwise. So we allow a laxity of sets of measure zero. Okay, so that's dealt with our stock of ordered vector spaces. Our claim was we're going to look at vector lattices. So the next concept that is required is that of a lattice. There are various ways to define lattices. Since we are starting with partial ordering, we will define a lattice in terms of what we have already talked about. So we take a partially ordered vector space, a partially ordered set X with partial ordering predecessor, and the set X is said to be a lattice if the supremum of every pair of elements, say X and Y, of X exists in X, and we denote that by X v Y, and the infimum of every pair of elements of X denoted by X wedge Y exists in X. Now, we've already defined supremum and infimum, so those only require the notion of partial ordering. So we can test now whether a set is a lattice, a partially ordered set is a lattice. And we are going to go through a stock of relatively well-known examples. We start off with a non-empty set X, and we denote Px by Px, the power set of X. As before, we can partially order the power set by set containment. So now that's a partially ordered set. Px is a partially ordered set. And for each A and B in Px, we have that A and B have a supremum in the power set of X, which is exactly the set union of A and B. And they have an infimum, which is the intersection of A and B. And let's just go through it. Let's do the upper bound verification here, just so that we see that this isn't, that I'm not just fudging things. So we have the two sets, A and B, and we need that A union B firstly to be an upper bound of that set. Well, A is a subset of A union B, and B is a subset of A union B. So firstly, A and B are both comparable with A union B, and A and B are both predecessors of A union B. So indeed, A union B is an upper bound for the set AB. And next, if we have a set C from the power set of X, so in other words, if C is a subset of X, and C contains A and it contains the set B, then it certainly contains A union B. So that tells us that any other upper bound of the set AB, of the pair AB, contains or is a successor of A union B, so it's comparable with it. And hence, A union B is the least upper bound or supremum of A and B. A more abstract example of a lattice. How about we take omega to be a set, and we've got X as above, and we've got the power set as above, and we take the maps from X into the power set of X. So for each omega, each little omega in omega, we associate some subset of X. And we can partially order the space with F, capital F less than or equal to capital G, if the set F of omega is a subset of G of omega for each omega in capital omega. Now, the lattice operations, well, supremum and infimum are the supremum of F and G evaluated at omega is F of omega union G of omega, and the infimum of F and G evaluated at omega. Note, the supremum of F and G is a map from omega to the power set of X, and the same for the infimum. So when we evaluate F inf G at omega, we need to find out what it is, and that is F of omega intersection G of omega. And thus makes the set of maps from omega into the power set of X a lattice. Some further examples of lattices. Well, how about the real valued continuous functions on the interval 0, 1 with pointwise operations? And it's relatively, well, let's have a look here. If we have two real valued functions, continuous functions on the interval 0, 1, or sorry, -1, 1, and we take the pointwise minimum at each, if we take the minimum at each point of those to define the value, we get a new continuous function on the interval -1, 1 that is an upper bound, and it is in fact the least upper bound of the pair. The same can't be said for the C1 functions on the interval -1, 1. Those are the functions which are continuous and have continuous first derivatives on -1, 1. This is not a lattice under pointwise operations. And this can easily be seen by taking the identically zero function, to certainly C1 on the interval -1, 1, and the function f of x equals x. And if one tries to find the least upper bound of the pair 0f, there is no least upper bound. There are many upper bounds for it, but there is no least upper bound living in C1 -1, 1. And intuitively, any such upper bound would have to have a corner at x equals 0. But you can show that abstractly as well, that there is no least upper bound here. And a simple computational example now, consider the set of 4 vectors 0, 0, 0, 1, 2, 0, and 2, 1. And this is a lattice under component-wise ordering, because we can take the supremum of 0, 0 with 0, 1, and we get 0, 1. We can take the supremum of 0, 1 with 2, 0, and we get 2, 1. We can take the supremum of 0, 0 with 2, 0, and we get 2, 0. And similarly, we can take the supremum of 2, 1 with any of the other vectors here, and we get 2, 1. And we can do the similar things for infimum. So it is indeed a lattice. Well, we are now at the point where we can talk about what a respace is, or a vector lattice. So a set is a respace if it has the following 3 properties. It needs to be an ordered vector space. And with respect to this partial ordering, it also has to be a lattice. So an ordered vector space that is also a lattice is known as a vector lattice or a respace. Some examples of them. Well, the reals with less than or equal to, Rn with component-wise ordering, Rn with lexicographic ordering, the continuous functions, the real-valued continuous functions over a topological space X, the LP spaces, the real-valued LP spaces of AE equivalence classes, and the last one I would want to talk about here is the set of maps from some set X into the reals with pointwise operations and pointwise partial ordering. And here, the supremum of f and g evaluated at x is the maximum in terms of real numbers of f of x and g of x. And we do this for each value x in x. And we can do similarly for the infimum. Now, let's talk a little bit about lattice completeness. So we start starting off with a partially ordered set. And we say that the set is order complete if every non-empty subset of X has a supremum and an infimum. Now, it's very easy to see that the reals is not order complete. And this requires, for your set X to be order complete, it requires the boundedness of it. So our function spaces that we talked about are not order complete, but when we start talking about the set operations on the power set, then we start getting order completeness. So the power set of a set X with set containment as partial ordering is order complete. And similar can be said for the space of maps from a given set omega to the power set of a given set. That again is an order complete lattice. The partially ordered set X is said to be Dedekind complete if every non-empty set that's bounded above has a supremum. So now the reals are Dedekind complete. Rn with component-wise ordering is Dedekind complete. The LP spaces are Dedekind complete. That's a bit harder to prove. Okay. And we can now weaken that yet further. We say that the set X is sigma Dedekind complete if we only require that non-empty countable subsets of X that are bounded above have a supremum. This comes in useful in some areas where we only want to work with sequences, not more general collections of elements in your set. And we note now, back at what we required for X to be a lattice, we only required that the supremum of each two element or each pair of elements had a supremum, or the supremum of each pair of elements existed. So these definitions here are given from the strongest constraint through to the weakest constraint on this page. And this is where we will leave the material for this week. Next week, we will start talking about bands, cones, band projections, and some things relating to components and weak order units in vector lattices. Thank you.
Thank you very much, Bruce. It was a very, extremely clear lecture and very well presented. Thank you so much for that. We still have time for questions, so I would like to invite the attendees to ask any questions if they have them. I have one unimportant question while the attendees are possibly thinking about their questions. At the last slide, when you defined completeness, I would imagine that you wanted this non-empty subset so that it nicely flows into the Dedekind completeness definition. But of course, for the second bullet point, we could also require any subset to have supremum and infimum, right? Because the entire
of course, yes. Yeah, you just want to remove. I just didn't want to get into pathological cases in definitions and things.
Right.
So if one starts out by assuming things to be non-empty, then you don't have to look at any special cases. You don't have to look at the set of upper bounds, because the problem is if your set is, you can, when you start looking at the empty set and you're looking at your set of upper bounds, you start having a problem because that's your whole space. Yeah. And now you want that to have a least element and things like that. So things start breaking. So you just have to be a little bit careful.
Yes, I agree that for the third bullet point, it's important that we only require this for non-empty subsets. Yeah.
So yeah, for the lattice one at the bottom, well, really, if you don't have any two elements, well, you've got nothing to check. So
Sure.
You haven't met the first condition. So.
Yes, of course. Yes.
Yeah.
I see that Partha is asking a question. I'm going to unmute him. Partha, you can go ahead and unmute your microphone and ask the question.
No, what I want to say along with Zurab is, in the second bullet point, if you take an empty set, its supremum is still the smallest element, and its infimum is the largest element. So it's order complete if every subset has a supremum and an infimum.
Yep. So yes, certainly X, the second bullet point, you can throw away the empty.
Correct.
The non-empty requirement, yes.
Yes.
So
yes. The distinction comes in the extra.
In the third bullet point,
Yeah.
when you
correct.
when you're starting to assume boundedness.
Correct.
Yeah.
Correct.
Since we're talking about the empty set, at the beginning you also assumed the set to be non-empty when you define the partially ordered set. Now there is so the notion of a partially ordered set can be seen as a special case of the notion of a category. And then one generalizes from partially ordered sets to categories. The notion of supremum becomes so-called co-limit. And it is nice when your categories are complete, so you have all co-limits. But if we exclude the empty set among our structures, then our categories of structures will no longer be complete because they will not have a co-limit of the empty diagram. So for category theories, empty set is also regarded as a partially ordered set.
For partial ordering, we don't require it to be, you don't really need it to be non-empty.
Yeah.
Because everything trivializes.
Yes. Yes. There's exactly one relation on the empty set, which is the empty set. And that is trivially reflexive.
Reflexive, transitive, and antisymmetric, yes.
And whatever you can think of.
There is another question. Any software recommendation for simulation? It's a question from Emmanuel Diaz.
Sorry?
There is a question in the chat which reads, any software recommendation for simulation?
I honestly don't know. I'm not aware of any specially set up software, but the economists actually do use a whole lot of these notions in mathematical economics. In particular, they do work in Rn with component-wise ordering. So some of the econometric software may have some of these tools built in for doing it on Rn.
I think Statistica or those old BMDP, they also had it because they wanted to work with order statistics.
Yeah, it's fairly likely that they would have it.
Yes.
And as I said, a whole lot of econometrics is done using partial ordering on Rn, the component-wise partial ordering. So
if I could also
stands
add,
to reason that,
Sorry, the connection is delivering our voice slower than we speak, so I often interrupt. I apologize for that. I was just saying that if I could add, if somebody is interested purely about lattices, there is a software called Universal Algebra Calculator, which I attached the link in the chat, that allows you to do various operations on lattices. And also, more importantly, applications of lattices for universal algebra.
Oh, okay. That's okay. Good to know.
Let's see if anyone else has any further questions. Perhaps, Bruce, could you maybe remind us, not too formally, just intuitively, the definition of measurable functions, because you used it in one of the examples.
Yes, and in actual fact, towards the end, we will work with it a little bit more. So measure is an abstract way of looking at the content of a set. So you have a countably additive set function defined on a class of subsets of your given set called the measurable sets. They form a sigma algebra or a countable algebra. So an algebra where you allow countable operations. And this operation on those sets needs to be countably additive. And you typically assume that it takes on at least one finite value. And that's the essentials of the starting point for measure theory, and the starting point for abstract integration. And so a function is measurable if the inverse image of open sets, we're looking at, let's say, real valued measurable functions, the inverse image of each open set in the reals should be in your algebra of measurable sets, or sigma algebra of measurable sets. So that defines your class of measurable functions. And then on those functions, we can define an abstract integral for starting off with non-negative functions. So functions which only take values in the non-negative reals. And those integrals can always be shown to exist with respect to your measure. And if the integral of your functions, if you can also show that, as we will show actually in the next lecture, if you are in a vector lattice or respace, you can always decompose your elements into a positive part and a negative part. So the positive part lives in your positive cone E plus, and your negative part has minus your negative, well, it lives in the positive cone, and your original object was the positive part minus the negative part. And that is a property that is always available in vector lattices. And that underlies a whole lot of integration theory, because what you actually do is you integrate over the positive part and the negative part of your function and glue those together. You subtract them to get back to your function. And
thank you very much
we will talk. And as I said, if you want to make these classes into nicely behaved objects that work well for stochastic processes and things like that, you need to look at AE equivalence classes, or if you like, almost everywhere, or with probability 1 the same. So you equivalence things so that the sets where they, or the set on which two functions are different, if you identify the two functions, they can only differ on a set of probability 0. And probability is a special case of measure.
There is a question in the chat. Will this
Can
course deal directly?
Bruce?
I'm reading a question from the chat. It was before you raised your hand, so I'll let you ask your question after that. Will this course deal directly with any applications in physics, or will it largely be pure mathematics content?
For the mini course, it will, as I said, we started out with getting to the point of vector lattices. The next week, we will be looking at the operator structures on things like band projections, some special classes of subspaces of these spaces, and various maps that are needed there to do stochastic type processes. We will not be looking at physics per se, no. The aim here is to try and get towards stochastics. And so it's quite focused in that direction. But if you want to do physics in a partially ordered space and study it in that sense, the tools will be very similar.
Thank you for that. And the last question from Partha, you had your hand raised.
No. I just wanted to say, Bruce, well, regarding the intuition, can this be suggested like if we take the set of all real valued continuous functions on reals, and then we have only two operations. We take countable joins and countable meets, and then go on doing these operations countably many times. Then what lands up, the total set that lands up is precisely the class of measurable functions. So you take countable joins first, then you take countable meets, then you take countable joins and countable meets, followed by countable joins, and so on. You carry on like this.
Yeah, but you have to
So,
do it infinitely.
yeah. Correctly. Yes, correctly. You go on countably many times, and what you get is precisely the class of measurable functions.
And then this takes on back to your F sigma
Yes.
and G delta sets. Yeah.
Yes. The whole Bayer hierarchy.
Yeah.
And what was the starting point for that, Partha?
So you have real valued continuous functions on
I see.
reals,
Mhm.
and then you take its countable joins of such, and then countable meets of such.
Mhm.
Then you carry on with these. So these are the two
So
processes
joins
by
and
which.
meets are as were defined in this lecture, right?
Yes.
Yeah.
And you
But
go on
the
taking
problem
these.
is you
Yeah.
have to carry on. This is well, yeah. That's the issue is that you never quite get there
Yeah.
if you stop at any point.
Yeah. You stop at omega
So,
1. Yeah.
yes, exactly.
Mhm. Wonderful. Thank you very much, Professor Watson, for the wonderful lecture. And so we look forward for the next one, which I believe will be next week.
Yes.
Thank you.
Great.
Thank
I
you,
will
Bruce.
see you all at 2:00 next Wednesday.
That's
Yeah.
right.
And thank you for listening to me. And I hope you enjoyed it.
Thank you.